This is the lecture number 2 of chapter units and dimensions, and here in this video we are going to discuss about the dimensions of physical quantity, dimensional equation, types of variable and constants, and uses of dimensional equations. So let's get started. So first topic here is dimensions of a physical quantity. So in lecture number 1 we have learned that we can express all the derived units in terms of 7 fundamental quantities. So these 7 fundamental quantities are called as the 7 dimensions of the physical world, and we denote them with square brackets like this. Now let's see the dimensions of these 7 fundamental quantities. The dimension of length we write like this, the square bracket, and inside we put L. And the dimension for mass we write as a square bracket, we put capital M inside. The dimension for time we represent with square bracket, and inside we put time. So dimension for electric current we represent with square bracket inside A. For temperature, dimension for are like square bracket K, and the dimension of luminous intensity square bracket CD. So the dimensions of a physical quantity are the power to which the base quantities are raised to represent that quantity. So let me explain this with an example. We know the volume of a cube is equal to length cube. So we can write the dimension of length. We know the dimension of length is L. So in terms of that we can write the dimension of volume in terms of this length is equal to L cube. So here we do not have mass and we do not have time. So we put the dimension of mass m raised to power 0, and for time also we put t raised to power 0. So to write the dimension of volume we have to include mass and time also. So we first will put a square bracket and then mass raised to power 0, t raised to power 0, and L raised to power 3. So these are the dimensions of volume. So we know the mass raised to power 0 is equal to 1, t raised to power 0 is also equal to 1. So the dimensions for the volume, we have to write this L first, m0, L raised to power 3, and t0. So the volume is equal to this, and this is known as the dimensional formula for the volume. Similarly, we can find out the dimensional formula for other derived units like area, velocity, force, and so on. Similarly, we can write the dimensional formula for the velocity. We know the velocity is equal to distance divided by time. So distance dimensions are L and time has dimension t. So here we do not have any m, so we can write the dimensional formula for velocity as m raised to power 0, L raised to power 1 because we have one exponent here, and t raised to power, it will go up, -1. So this is the dimensional formula for the velocity. So if we see this dimensional formula of the velocity, it is telling us two things. Number one, it is telling that the unit of velocity depends upon unit of length and time, and it is independent of the unit of mass. Second, it is the power of length and t. Here the power of length is 1 and the power of t is equal to -1. So the dimensional formula of any physical quantity may be defined as the expression that indicates which of the fundamental unit of mass, length, and time enter into the derived unit of that quantity and with what power. As in the velocity case, the power of mass is 0, the power of length is 1, and the power of time is minus 1. The second topic here is the dimensional equation. What is that? This is very simple. An equation obtained by equating a physical quantity with its dimensional formula is known as the dimensional equation of that physical quantity. For example, if we take the velocity, the dimension for the velocity were m0 l1 t minus 1. If we represent this velocity with small v enclosed in square bracket, and then we equate this v with the dimensional formula of the velocity, then we'll get an equation. We will get an equation like this: m0 l1 t minus 1 and square brackets. Then this equation is known as the dimensional equation. So in order to find the dimensional formula for a particular physical quantity, you need to remember the formula of that physical quantity. For example, suppose if we have to find the dimensional formula for the density, so you should know the formula of the density. We know the density is equal to mass divided by volume. The dimensional formula for mass is m with the square bracket, and the velocity. And for the volume, what is the dimensional formula for the volume? L cube. So we can write the dimensional formula for the density now. So here we have m raised to power 1, L raised to power minus 3, and time we do not have, so we'll put here t raised to power 0 and square brackets. So this is my dimensional formula for the density. Similarly, we can write dimensional formula for let me take force. So for that you should know the formula for the force. Force is equal to mass. For that you should know the dimensional formula for the acceleration. So acceleration we know is equal to velocity divided by time. So we know the dimensional formula for the velocity is L t minus 1, and the dimensional formula for the time is t. So we can write the dimensional formula for the acceleration from here. M we don't have, m0, L we have 1, so t raised to power minus this minus 1, and this also go up, this will also become minus 1 and square bracket. So we can write the dimensional formula for the acceleration as m0 l1 t raised to power minus 2 square brackets. So similarly, now we can write the dimensional formula for the force. For the mass we have m square bracket, and for the acceleration we have dimensional formula for this m0 l1 t raised to power minus 2. Now we'll combine these two and we'll see here we have multiplication. So m raised to power 1 plus 0 is 1, L raised to power 1 and t raised to power minus 2 and square bracket close. So this is the dimensional formula for the force. Now let's see 2-3 more examples. Let me take pressure. So pressure is equal to force divided by area. So we know the dimensional formula for force is m1. The dimensional formula for force is m1 l1 t raised to power minus 2. So dimensional formula for area is length square is L raised to power 2. So now we have to use the rules of exponent to solve this. So we'll get here m raised to power 1, L raised to power 1, and this is 2 down, negative 2 multiplied with t raised to power minus 2. So this is the dimensional formula for the pressure m1 L raised to power minus 1 t raised to power minus 2. So this is the dimensional formula for pressure. Now let's find the dimensional formula for the strain. The strain is equal to the change in dimension divided by original dimensions. So it could be length. So change in length means as the dimension of length we take length, and the original length also have the dimensions of length. M we do not have, L raised to power 1 and this will go up minus 1, t raised to power 0. So the dimensional formula for strain will become m0 l0 t0. So we can say this strain is a dimensionless because it does not have any value for m, L and t. Now let's see the dimensional formula for gravitational constant. So we know that gravitational force F is equal to G m1 m2 divided by r square. So from here we can find out this G is equal to force multiplied by distance squared divided by m1 and m2. We know the dimensional formula for force, which is equal to m1 L1 t raised to power minus 2, and for this distance r, we know the dimensional formula for distance is L, so it will become L square, and here the mass, and this is also mass, it will become m multiplied with m. So we can write this as, here we have 1 m raised to power 1, this will go up minus 1, this will also go up minus 1, and L raised to power this 1 plus this 2, 1 plus 2 t raised to power minus 2 square brackets close. So we'll get here the dimensional formula for G as m raised to power, this will get cancelled with this, m raised to power minus 1, L raised to power 3 and t raised to power minus 2. So this is the dimensional formula for gravitational constant. So like this we can find out that the dimensional formula for various physical quantities like moment of inertia, angular velocity. Now let's see the dimensional formula related to the heat and thermodynamics. So for that I'll take this specific heat capacity. The formula for the specific heat capacity is equal to quantity of heat divided by mass into temperature. The quantity of heat is a form of energy. So dimensional formula for heat is equivalent to the dimensional formula of energy, which is equal to m raised to power 2 t raised to power minus 2. So here divided by mass, the dimensional formula for mass is m, and the dimensional formula for temperature, which we measure in Kelvin, is equal to K. So we can write here m raised to power 1, here 1, here it will become minus 1, L raised to power 2, t raised to power minus 2, and K raised to power minus 1. So dimensional formula for heat capacity is equal to m raised to power 0, L square, t raised to power minus 2, and K raised to power minus 1. Now let's write the dimensional formula for electric charge. So we know the electric charge is equal to current multiplied by time. The dimensional formula for the current is ampere, and for T it is T. So we can write the dimensional formula for electric charge as m, we don't have, raised to power 0, L raised to power 0, T, and ampere. So like this we can write all the dimensional formula related to all physical quantities related to the electricity and magnetism, like electric flux, electric capacitance. We'll see all these dimensional formula in 12th standard. So third topic which I am going to discuss here is different types of variables and the constant. So we know the variables are those quantities which varies with time, and constant which do not vary with time. Let's see the different types of the variables and the constant. Here we have 4 categories. First one, dimensional variables, second one is non-dimensional variables, third one is dimensional constant, and fourth one is the dimensional non-dimensional constant. Let me explain these one by one. These are those physical quantities which have dimensions and they do not have any constant values. For example, area, velocity, force, pressure, etc. All these quantities have them. We know we can write the dimensional formula for all these physical quantities, and they do not have any constant value. So these are the dimensional variables. So next we have non-dimensional variables, means those physical quantities which vary, which are not constant with time, but they do not have any dimension, means they don't have dimensions and they do not have any constant value. For example, angle, specific gravity, strain. They do not have any dimension, but they vary with time. So all these are non-dimensional variables. Third physical quantities are dimensional constant. These quantities, they have dimensional formula. We can write the dimensional formula for them, but they are constant. They don't vary. For example, the gravitational constant is there, Planck's constant is there. All these have dimensions and they have constant values. Next, non-dimensional constant. No dimensions, but they are constant. For example, 1, 2, 3, 4, pi, e, all these have some constant value, but they do not have any dimension. The uses of dimensional equations. There are 3 uses of the dimensional equation. These are, so first one is to check the correctness of a physical equation. For example, if we have one equation and we want to check the accuracy of that equation, that whether that equation is correct or not correct, we use the dimensional equation. Let me explain this with an example. So here it is given, check the accuracy of this relation. The relation is half mv square is equal to mgh. So here m is the mass, v is the velocity, g is the acceleration due to gravity, and h is the height. So for that, first we have to write the dimensional formula for the left hand side of the equation and the dimensional formula for the right hand side of the equation. Then we will see whether the dimensional formula for the left hand side is equal to the dimensional formula for the right hand side. If they are equal, then the relation is accurate, otherwise this relation is not accurate. So first we will write the dimensional formula for left hand side, which is equal to half mv square. We know the half is a dimensionless constant, and the dimensional formula for m is mass, and the dimensional formula for the velocity is equal to lt minus 1 raised to power 2. So here we'll write, we'll combine these, we will get m l raised to power 2 t raised to power minus 2. So this is the dimensional formula for the left hand side. So let me mark this as equation 1. So now I'll take right hand side, which is equal to mgh. The dimensional formula for the mass is m. For the acceleration due to gravity is equal to the acceleration, which is lt minus 2. H is the height. The dimensional formula for height is equivalent to the length, so that is equal to L. Now we can write this as m L raised to power 1 plus this 1 plus 1 and t raised to power minus 2. So this will become equal to m L raised to power 2 t raised to power minus 2. So let me mark this as equation 2. If we compare these two, left hand side and right hand side, we'll see. So for the dimensional formula for the left hand side is m L square and t raised to power minus 2, and the dimensional formula for right hand side is also equal to m L square t raised to power 2. So we can say the dimensional formula for left hand side and right hand side are the same. So the given relation is correct. The second property or use of dimensional equation is to derive a relation between different physical quantities involved in a physical phenomena. So let me explain this also by taking one example. Derive an expression for the centripetal force F acting on a particle of mass m and velocity v and the radius of the circle r. So now we have to derive an expression for the centripetal force F, which is acting on a particle of mass m with velocity v, and this particle is moving in a circle of radius r. And here we do not know to what powers of mass, velocity and radius this force varies. Suppose that the force F varies as nth power of mass, which is m, bth power of velocity, which we take as v, and cth power of radius, which we take as r. So we can write this equation as F is directly proportional to m raised to power a, F is directly proportional to v raised to power B, and F is directly proportional to the R raised to power C. Now we will combine all these. So we'll get force is directly proportional to M raised to power A, V raised to power B, and R raised to power C. So we can remove this proportionality constant with equality by placing one constant K. So we'll write this equation as F is equal to K, M raised to power A, V raised to power B, and R raised to power C. Now we'll write the dimensional formula for all force, K, mass, V, and R. We know the dimensional formula for force is M1 L raised to power 1 and T raised to power minus 2 is equal to K is doesn't have any dimension, so I'm not going to write here. So M has the dimension of mass raised to power A. The velocity dimension is LT minus 1 raised to power B, and radius has the dimension of length raised to power C. Now we can write this as M1 L1 T raised to power minus 2 is equal to here M raised to power A, L raised to power B plus L raised to power C, and T raised to power minus B. Let me mark this as my equation number 1. So now we'll find the values of A, B, and C. The power of mass will equate with the power of mass in left hand side, and similarly the powers of lengths we will compare, and time also will compare. The mass here is raised to power 1 and here it is A, so we can write this as 1 is equal to A. The power of length here is 1, and here we have B plus C, and here the power of time is minus 2, and here we have minus B. So from here we'll get A is equal to 1, and from here we'll get B is equal to 2. Correct. Now we'll put this value of B here, we'll get C. So 1 is equal to 2 plus C. So C is equal to 1 minus 2, which is equal to minus 1. So A is 1, B, C is minus 1, and B is 2. We'll put all these value in this equation number 1. So we'll get here F is equal to K, M raised to power A is equal to 1, V raised to power 2, and R raised to power minus 1. So we can write this formula F is equal to K M V square divided by R. So this is the formula for the centripetal force. The third use of dimensional formula is the conversion of one system of unit to the another system of unit. In the previous lecture we have learned the four system of unit. CGS system is there, MKS system is there, FPF system, and SI system. So we can use the dimensional equation for the conversion of one system of unit to another. For example, if we want to convert the CGS system to SI system, then we can use this dimensional equation. So for that we use this formula N1 U1 is equal to N2 U2. So this also we have discussed in lecture number 1. So here we have taken two system of units U1 and U2. Let's take the mass in this system of unit is equal to mass of a physical quantity is M1, the length is L1, and time is T1. Similarly here for this system of unit, the mass we represent with M2, the length we represent with L2, and time we represent with T2. The power of that physical quantity will be same. These powers of mass, length, and time for both the unit of system will be same. Let me take the power of mass is A, the power of length is B, and the power of time is equal to C. We'll put all these values here in this equation. So we'll get N1 so dimensional formula we can write it as M1 raised to power A, L1 raised to power B, T1 raised to power C, close the bracket, is equal to N2 as it is M2 raised to power A, L2 raised to power B and T2 raised to power C. So we can find out this value N2 is equal to N1, M1 raised to power A, L1 raised to power B, T1 raised to power C divided by M2 raised to power A, L2 raised to power B, T2 raised to power C. So we can combine them. We can say N2 is equal to N1 M1 divided by M2 raised to power A, L1 divided by L2 raised to power B, and T1 divided by T2 raised to power C. So like this we can convert the one system of unit to the another system of unit. In next video we will do the numericals related to lecture 1 and the lecture 2. This is all for today. Thank you for watching my video.